Okay, so it's time to get started with our last session of the conference. So yeah, this is our afternoon session. I see people are streaming in, so maybe we'll let folks come in for just a minute. Yeah, I think we're good to start. So fantastic. So our first talk of the session is going to be on Blitz by Lucas Neuer. So looking forward to the talk.
Okay, thanks. So hello again. I'm Lucas Aumeier. I'm a PhD student at the Technical University of Vienna. And as I promised you yesterday, today I will talk about Blitz, secure multi-hop payments without two-phase commits. So this is a joint work that we did together with Pedro Moreno Sanchez, Aniket Kate, and Matteo Maffei. So maybe to briefly outline what I'm going to talk about. So Blitz is, in a nutshell, a new multi-hop payment paradigm for payment channel networks that is more efficient, smaller in size, reduces the collateral lock time from linear to constant, and is secure against certain type of attacks compared to like more prominent schemes as, for instance, Lightning. Okay, so let me jump in with some motivation and background. So again, most permissionless blockchains suffer from the same issue, scalability. We have this global data structure called the blockchain. And in the blockchain, basically every transaction is recorded. And on top of this, we run a global consensus in which basically everyone checks the whole blockchain and verifies the transactions. So this creates a bottleneck, actually. And for instance, if we look at Bitcoin, the transaction rate is very low, about tens of transactions per second. And if we compare it with more centralized payment systems, such as, for instance, Visa, they can manage tens of thousands of transactions. So there's actually quite a large gap. And so one of the ideas is off-chain solutions. And the intuition behind it is basically that instead of putting every transaction on the blockchain itself, we try to exchange as many transactions as we can off-chain, and we use the blockchain itself basically more as a fallback, so if there are any disputes. So specifically in this talk, again, I want to focus on payment channels, and they work like this. So let's look at three phases. We have Alice and Bob. They anticipate many payments between one another, so what they can do is they can open a payment channel. They do this by locking some coins in a multisig address, so they put a transaction on chain where they lock some money, and then from this transaction they create what we call a state. This is basically a transaction that spends from this locked money that they put and redistributes the money back to themselves. So this is the state 0, right? Once they did this, what they can actually do is they can update the channel, and they simply do this by creating a new state where they redistribute basically the balance, and they can pay one another back and forth. And they can do this as many times as they wish. And once they're like happy, what they can do is they can close the channel. And they do this simply, one of the parties sends the latest state to the blockchain, and they get their money back. And you will notice that with payment channels, two parties can perform arbitrarily many payments between one another, and only two of them will end up on chain. Okay, so this is still not an ideal solution, right? Because if you were to use only payment channels, you would need to open a payment channel to every person that you potentially want to interact with, right? And this is unfortunately not feasible, since for every payment channel, what you need to do is you need to lock up some money that you cannot use otherwise. And you also might not know in advance whom you actually want to pay to in the future. So it's also not feasible to open up with everyone, and you will need to put transactions on chain. So we actually need to have a better solution. And this is where payment channel networks can come in. And the idea behind them is that we actually take the payment channels and we link them to form a network. And then in this network, you use something that is called multi-hop payments, where basically any two users that are connected via path of channels can perform a payment between one another. And again, the most prominent example for this is the Lightning Network. As of yesterday, there was like 94 million dollars worth of Bitcoin locked in the Lightning Network. They had like 18K nodes and 87K channels. So let's now briefly jump into how the multi-hop payments work in the Lightning Network, such that we can see how they can be improved. Okay, so suppose Alice wants to pay 5 coins to Dave via a path of where there are the 2 intermediaries, Bob and Carol. So what they do is they perform the following steps. So first, Dave samples some pre-image X, hashes X to Y, and sends Y to Alice. Alice then goes ahead and sets up an HTLC, which is a hashed time lock contract with Bob, holding these 5 coins, and an HTLC encodes the following logic. Either Bob gets the money if he knows a pre-image X, such that X hashes to the condition Y, or Alice will get the money back after some timeout. In this case, the timeout is 3T. Okay, then Bob will set up the same HTLC with Carol, although the time now is only 2T, and I will get back to this, why this has to be the case. And finally, Carol sets up an HTLC with Dave that is the same, except now the time is only 1T. Right, so once this has happened, what Dave can do, since Dave knows the pre-image X, Dave can actually open the HTLC and redeem his 5 coins. However, in doing so, Dave actually reveals X to Carol, and then Carol can redeem the 5 coins from Bob, and then Bob can redeem the 5 coins from Alice. And the payment is successful. Okay, so this is in a nutshell how the multi-hop payments work in the Lightning Network. Okay, so I want to point out a couple of things here. So first, this payment is executed in 2 rounds. We also call this a 2-phase commit scheme. And what I mean by round is basically a sequential pairwise communication from the sender to the receiver or from the receiver to the sender. So as we can see, we have the first round, basically, where the money is locked in the HTLCs. And we have the second round, where then the money is again unlocked. So 2 rounds of communication. The second thing I want to get back to is what I already briefly mentioned, is this time lock, right? And the timing, as I mentioned, grows from Dave, the receiver, to Alice, the sender, and it increases by 1T for every hop. So it's asymptotically linear, and since it's increasing, we also call it a staggered lock time. And let me also point out that in Lightning, this small t is actually 1 day. So the timeout increases by 1 day per hop. And the reason why this needs to be there is if you imagine that, for instance, a malicious, so if the timing was the same everywhere, a malicious Dave could actually redeem his 5 coins at the last possible moment, so just seconds before t would expire. And this would give Carol not enough time to react and also redeem her coins from Bob. So we need to actually give Carol more time to redeem her coins. So this is the reason for why we need this. Okay, so let me sum up here some properties and also some drawbacks of the Lightning payments. So first of all, I want to point out that this is actually already quite a nice solution to the scalability issues, because now we can really we don't need to open a payment channel to everyone, but we can just use a more sparse network, and we can actually use the paths of channels to pay to one another. Secondly, it also achieves something that I'm going to call here like balance security. And on a very, very high level, it just means that the honest users, they are not at risk of losing their money. And finally, it also achieves some sort of privacy. And again, I put it here in quotation marks. On a high level, you can think of it as the users on the path, in case that there is a successful payment, learn only about their direct neighbors, not about who is on the whole path, and they also learn about the payment amount. So, but importantly, they don't learn the whole path. Okay, so now to some drawbacks, and I already mentioned 2 of them. So first is the staggered collateral lock time. This is an issue because in case that the payment does not succeed, and this can happen for multiple reasons, right? So there can either be like users being offline or network outages, but it could even be that the users are malicious and actively trying to like grief the network. So if the money is locked up for a longer time, this means that the network throughput is actually decreased. So it can become problematic. The second point I also already mentioned, it takes 2 rounds. And of course, it would be both in theory and practice be nice to manage it in 1 round. Also, another point I want to briefly mention is that it requires the HTLC scripting requirements. So again, you rely on the blockchain supporting the hash locks for implementing this. And finally, there is also this wormhole attack that was pointed out by Malavolta and others, where in a nutshell, malicious users that are surrounding honest users can steal not their funds, but their fees, basically. And so this is also another issue that is in the Lightning payments. So now the question that we ask ourselves is, so can we basically come up with a payment scheme that has, of course, the nice properties of Lightning, but also increases or improves on these drawbacks? And can we do this in 1 round? So, and obviously, so we answered this in a positive way, and I want to go over over the construction now. And let's do it in a way where we start out with a simple solution approach, and then we see what are the problems with those, and we try to improve it until we get to the actual construction. So one very simple way of doing this, and keep in mind our goal is to now do these payments in 1 round. So one simple way of doing this would be like this, right? This is really, really simple. So we just go ahead, and the first step is that Alice just gives 5 coins to Bob and says, please forward this to Dave, right? And then Bob goes ahead and pays 5 coins to Carol, and Carol pays 5 coins to Dave. So and this is actually something that was also proposed in this paper, Interledger Payments. The obvious drawback with this is that it relies on the intermediaries being honest, right? So it could be the case that Bob is malicious and the attack is not very complex. Simply what he needs to do is he just can go offline after receiving the 5 coins, and the money will not reach Dave. So this is an issue. So basically, towards a solution, what we could try and do to prevent this is we could try and introduce a way for Alice to step back from the payment if the payment doesn't reach Dave. So let's actually try and do this. So we do something that kind of looks like this. So Alice still pays to Bob, but Bob only gets the money after some timeout capital T, right? And additionally, we introduce a way for Alice to step back from this payment. So basically, this is the error going back to herself. And this she can use in case that Dave doesn't receive the money. So they set this thing up, right? And then if it reaches Dave, Dave sends back the confirmation. Alice will simply go idle, and the payment will go through. If it doesn't reach Dave, then Alice can step back from the payment. So still this has some problems, right? So there are actually 2 problems, right? So the first one is only Alice should be able to step back from the payment if it doesn't reach Dave, whereas here everyone can step back from the payment. Or the other issue is that basically the timeout is again the same, and potentially the subsequent users will not have time to react. So what could happen, for instance, is that they set this up, and then moments before this timeout capital T expires, a malicious Bob simply refunds himself, basically, which would cost, in this case, Carol to lose 5 coins. So we need to think of something a bit more clever. And again, one way, and I promise this is the last one before we reach actually the solution, is we could actually reintroduce in some way some hash locks, right? So if we condition the refunds on some hash lock to which Alice knows the pre-image, right, we already would have solved the problem that only Alice can trigger these refunds. And to get rid of the problem that the subsequent users have enough time to react, what we would do is we could, of course, still introduce this staggered timeout, right? So we could give Bob just a bit more time to react and then Carol even more time. This seems to work, right? But it doesn't solve the issues that I pointed out in the beginning. So we still have the same scripting requirements as the Lightning Network, and we also have a collateral time that grows linearly. Okay, so now let's talk about what is the actual solution. So how do we overcome this problem? And we call this the pay or revoke paradigm. And basically the way it works is as follows. So Alice at first defines a timeout capital T, which is independent of the path length. Okay, then Alice creates a transaction which we call refund enabling transaction, or short TXER. Right, this is a transaction that Alice does not put on chain, so she keeps this off chain. And this transaction has some outputs. Actually, it has one output for all of the users except for the receiver, Dave. Right, so 3 outputs. And these outputs contain a very, very small amount, epsilon. So you can think of the smallest possible amount. So like 1 Satoshi or maybe 1 dust or whatever, right? So it's a pretty insignificant amount. Okay, so now what Alice does is she sets up a contract to Bob in the following way. Either after this time, capital T, Bob receives the money, or before this time, Alice can refund herself, but only in the case that she before published the transaction TXER. So how can we ensure this? This is where these epsilon outputs come into play, right? We can actually make the refund transaction so that it takes this additional input, in addition to these 5 coins that we locked up in the channel, it takes as input this epsilon output that is in the transaction TXER. Right? And this ensures that the refund transaction can only ever be valid if both of the outputs that it spends are on chain, right? So we really require this transaction TXER to be on chain. Okay, so they set this up, and then Bob actually sets up the same thing with Carol, but with the refund transaction being dependent on his epsilon output of TXER. And finally, Carol does the same with Dave with the 3rd epsilon output. Okay, so and this is basically the payment. So now it's more or less done. What we need now is only that Dave sends back the confirmation, right? So Dave sends back, I received a payment of 5 coins that is conditioned on this transaction TXER back to Alice. And if Alice sees, okay, the transaction that Dave sent matches the one that I created in the beginning, then she's fine. She can simply go idle, right? She will not post the transaction on chain, and she can be sure that after the time T, Dave will automatically receive the money, right? Because the refund in the channel Carol Dave is conditioned on this transaction TXER being posted on chain. So if it's not posted, Alice is sure that Dave gets the money. Right. In the case that Alice does not receive the confirmation, she of course wants to step back from the payment, right? So she doesn't want to pay someone when it doesn't reach Dave. So what she does is she simply puts this transaction TXER on chain before this time capital T, and then everyone, right, because now the epsilon is on chain, everyone can actually refund the channels and the payment is reverted, right? And the thing I want to highlight is, and this is also why we can have a constant timeout T. It doesn't grow in a staggered way, and it's not linear, right? So it's really a constant time. And the reason why we can get it is because everyone will see the transaction TXER going on chain at the same time. This is really one of the key points. Maybe also let me finally point out that why the intermediaries are okay with this, right? So how is an intermediary sure not to lose money? And the reason for this is also quite intuitive, since basically an honest intermediary will construct his refund transaction on the same TXCR as his left neighbor, right? So this implicitly means if his left neighbor can refund, he can also refund. So this is also why the intermediaries are safe. Okay, so there's a bit more to the scheme that you can look up in the paper. For instance, we present a way on how you can do we call it a fast track for payments. So if you don't want to wait until this timeout capital T, right, you can introduce an optional second round of communication such that the payment goes through immediately, right? So before we had one round, but you had to wait until this timeout T. And if you have an optional second round, it goes through instantly, or more or less instantly. The second one is you can also, if the users are honest, you can also implement a mechanism such that the payment is reverted without posting the TXCR. And I also want to briefly mention that privacy, right? Because if we share the TXCR, which basically contains an output for all the users, and we don't kind of hide who these users are in some way, then everyone will learn about the whole path. So how we can prevent this is, instead of putting the actual addresses in this TXCR, we can use stealth addresses to kind of hide the identities of the users on the path. So feel free to check out the papers for more information on this. Finally, I want to talk a bit about some comparison and evaluation results. So we compared our scheme to Interledger Payments, Lightning, Anonymous Multi-Hop blocks, and our scheme, right? And I want to briefly point out that before, what you had to do is you either had to decide, do you want balanced security and 2 rounds, or do you want to have 1 round and no balanced security? And now we can actually have both. And as I mentioned, we reduced the collateral lock time to constant. We are not susceptible to this wormhole attack that I mentioned, and we also don't need hash locks to implement this scheme. So for the evaluation, we did kind of 2 things that I want to mention briefly. So first, I want to point out that the Blitz contract is actually 26% smaller than a Lightning contract, the HTLCs. So this would allow us to potentially put more concurrent payments per channel. And the intuition behind this is a transaction has a limited size, right? So you can only put so many HTLCs in one transaction. But now if you have a smaller contract, you can of course put more of these contracts in the transaction. And further, we did a simulation on the Lightning snapshot, where basically we took a snapshot of the Lightning network, we simulated some random payments, and we simulated that some of them are being disrupted, either by users being offline, or they could be malicious or whatever. And then we looked at the effect of constant versus staggered collateral lock time, right? Because obviously the money that is locked for this time cannot be used for further payments. And we took a look at how many payments failed actually in consequence of this. And what we found is that in Lightning, actually, between 4 and 33x more payments failed due to this additional collateral lock time. So to sum up, we have this new multi-hop payment paradigm. We achieve it in 1 round of communication. We reduce the contract size. We reduce the collateral lock time from linear to constant, and we are secure against the wormhole attack. We only require signatures and time locks. We also gave the simulation to show the advantage of constant collateral. We modeled it in the UC framework, and I also want to point out that it is compatible actually with the Lightning network and Lightning channels. Maybe also a quick highlight of some follow-up work that we did from this. So you can check out the paper Thora, which will appear in this year's CCS, where we basically channelized the concept of Blitz to allow atomic updates on non-path topologies, so basically any topologies of payment channels. And finally, Donna, which is a virtual channel scheme that uses kind of Blitz to achieve virtual channels over any number of hops. So thanks, and happy to take any questions.
Yeah, very nice construction. Are there any questions?
So that refund transaction, right? So Alice has to always put it on chain, right?
Alice has to put it on chain, yes.
So let's say Carol doesn't want to proceed. It means that Alice has to go on chain, right?
So
if you don't get HTLC's refunds for free off chain, as you would in Lightning.
Right, this is true. So this is kind of one of the trade-offs is that if there's really one malicious user, so not in the case that someone goes offline, then you can honestly revert, right? But in the case that Carol is actively malicious, then yes, Alice has to put this transaction on chain. But actually only this transaction because the channels then can optimistically update themselves.
Oh, same question. Wow, okay.
Hi, I have a question. You said your paper on CCS will work for any topology. What do you mean by any topology? Can you work for cyclic directed graphs?
So what I mean by this is now, if you look at the payment, at the Lightning Network, right, you have a large number of nodes and channels, right? And Lightning payments and also Blitz only works on like really paths. So Alice, who wants to pay to Dave, needs to be connected via Bob and Carol. So with Thora, what you could actually do is, you could update channels that are not even connected. So let's say you have the channel Alice and Bob, and you have some other channels like Carol and Dave, but Bob and Carol, they don't have a connection, for instance. So it could be, or you could even, like branch out. So they update the channels Alice Bob and Alice Carol, and so really any topology, yes.
Okay, thank you. I have another question. Do you think your technique can extend to cross-chain payment channels?
That's actually a very good question. So the thing with this is that really the atomicity on the refund, right? It relies on this transaction being posted on chain, right? And all the other transactions need to refer to this one. So the problem with using it cross-chain is that on another blockchain, right? If you have Bitcoin and then Ethereum, for instance, on Ethereum you would need some way to refer to this blockchain and somehow convince, the smart contract or whatever on Ethereum that this refund enabling transaction was posted on this chain. If you have something like this, then it could work, but like just out of the box, it unfortunately won't work.
Thank you.
So I have one question on just the routing mechanism. So it sounds like in Blitz, Alice actually has to know the path that she will take to Dave.
Yes.
It's not that the path can be adaptively chosen by the participants along the way.
Yes, this is correct. So you really have source routing.
Source routing, yeah.
Yeah, which is, it's also true currently in the current Lightning implementation that you also have source routing, but here it's really a requirement, yes.
Here it's kind of inherent, right? Do you think there's any hope of eliminating that?
Honestly, I currently don't really see how, because you really have this transaction that you need to make up front. So it's not trivial, right? But maybe there's some way of coming up with a clever way of, dynamically adapting this transaction or so. But I currently don't see a simple way out, no.
Yeah, makes sense. Excellent. Thank you very much.